Morning, everyone. I wanted to admit to you, the other day when I forgot a couple things with John. Like I forgot, when I told him he had to leave because of that, he hadn't taken the test. I forgot to tell him that we were going to do a lesson that day too. And then another thing I forgot to do on that same day was I forgot to record the 4.1 lesson, kind of because it also came midway through. So anyway, I do have one day that I didn't get recorded, and that's the 4.1. But I did pick up yesterday, and I'm back on track. So it was one of the few days I forgot to do that. So there's a line for it, but there's no link, and that's the reason. Okay. I like that real nonchalant. Yeah. Okay. I'm just hoping this isn't going to start a new trend, but you never know. So let's start with questions about exponential functions. The that every other odd assignment from last time? Ought to go, Christina?
I just have a quick general question.
Yeah.
Am I agree that with the compounding space and the regular one, a person can use the regular one to do just a modification of the compound interest one? It doesn't really matter. Like when you do compound interest problem,
Right.
you could use the regular interest.
By that you mean the regular, you mean the one that's 1 over n?
Yeah, because it's
yeah, you could, but then n would have to be infinity, kind of.
Right.
But yeah, they really are the same formula. I think that's what you're getting at. Only one is modified to be compounded every, continuous, yeah. And then with an infinitely small time interval, yeah. Not quite. When you let me just okay, can we quiet down, please? I'll tell you what, to make this a little easier, give me a second. I'm gonna pull that file up from last time, and I want to show those two formulas, and then I can talk about them a little bit better. That was what, the 4.2? Yeah, well, they're kind of on the same page. Yeah. Okay, so you mean, are these two formulas really the same? If n becomes e. Not quite. What becomes e is 1 plus 1 over n part of this to the n. You could think of this as 1 plus 1 over n times r here to the n raised to the t. The 1 plus 1 over n to the n, that's the e part. So it's not just the n, but you're right. These two guys are really identical. The only reason this one can be simpler is because if you take n to be an infinitely small time interval, because that's what n is, how many times you compound it? It's an infinite. Then the 1 plus 1 over n to the n part becomes an e. Notice the r still is in the formula, but there's no n anymore. It's because 1 plus 1 over n to the n, which I had earlier in this presentation. Actually, that part does become e. Yeah. So the bottom line is, if you're doing continuous compounding, you need to use the top one, and if you're doing any other kind of compounding, you need to use the bottom one. Yeah. 9? Sure. Okay, number 9. 4.2, number 9. X to the 2/3 power is equal to the cube root of e squared. So I'm going to rewrite that this way. Is there any way to rewrite this cube root of a square? You can think of the power as a numerator of a fraction, exponent fraction, and the root can be a denominator. So really, isn't this e to the 2/3? And if you look at this, does this tell you something? X to the 2/3 equals e to the 2/3. It's almost a logical problem. Can you see that x and e have to be the same?
We just did plus and minus.
Why plus and minus? So they have the plus and minus on the e? Yeah, and here's why. Because if you use the original notation, if you had a negative e here and squared it, it would become a positive, just as a positive would. So it's because of this thing right there. So yeah, I really should have a plus negative there. So a negative and a positive e would both do the same thing here. And you can't see that from that's the trouble with my little technique right here. It didn't work. Anybody else? Questions of Fortune? So it doesn't sound like that was too. That's even though exponential functions are not usually one of the things that are the best at coming back. You must have been able to recall those pretty well. Okay, this one's going to be fairly short and sweet. I've already spilled the beans partly on this. How do you take the derivative of exponential functions? And now let me warn you of something. This statement that I have at the top of the page here, let me divide that, is not in the book. And in just a few minutes, I'm going to get to the one in the book. But it's important that you see this first, I think. So, here's what it's saying. If you want to take the derivative of some exponential thing, a to the x, that's a generic, that's the same guy we were working on the first 2 days of this chapter, a to the x, where a could be anything. Then the way to do it is this. First of all, it's equal to itself, multiplied by the natural log of the base, whatever the base of that exponential function, in this case a. So I'll just say that again. If you're going to take the derivative of some exponential, it's equal to itself multiplied by the natural log of its base. Okay. Now, I did an example. I should be able to take this function 10 to the x and find its derivative based on that. What do? The derivative of that is equal to itself multiplied by the natural log of its base, which in this case is 10. All right, now you can look up, how do you look up the natural log of 10? That would be a calculator thing. So now you would, if you got a calculator handy, you would do, you probably got to hit your ln x, and if you got a graphic calculator, then you got parentheses, and then you would put the 10 in there. Hit enter. You should get something like 2.302, I think. By the way, what does natural log mean again? Can you remind me? Well, I guess we haven't done logs yet this year, but that means e to what power is 10. So what you guys found when you did that natural log of 10, you were telling me what exponent has to go on e for the answer to come out to 10. Check it out. Do e to the x and put this number in and see if you get 10. And of course
except it might be more exact than 2.302, but you should get something really close to 10, right? Okay. So there it is. The answer is that number, 2.302 times 10 to the x. No, we can't do any better than that. That's it. And can I multiply this by 10? No. That 10 is not free to be multiplied. That has to stay with its power. So that's really as good as you can do. Okay, now the really good news is where this leads to. What happens when the base is e? And the answer, wonderful things. Because how do you take the derivative of an exponential? It's equal to itself times the natural log of its base. And what's the natural log of e? That is, what power do you have to put on e to give you e? E to the what power equals e? So the natural log of e is just 1. And so, what's the derivative of e to the x? E to the x. You know that I am my own grandpa song I was telling you about? I am my own derivative. E to the x screams out, okay? But, do you notice that you really had to do this? There's a little more going on than just self. You have to really multiply by the natural log of the base. That's why I showed you that other one first. So, anyway, in the future, you don't have to do this because every time you have an e to the x, it's always going to be times 1. And so I'm not requiring you to do this. I just want you to know that that's really what has to take place in the background. And what happens when the base is not e? Oh, then you have no choice. You've got to use this formula. You got to use this one. So when that base is not e, you just have to do this. When it's e, it simplifies wonderfully. And now, let's do this example at the bottom of this page. What if we wanted to differentiate e not just to the x, but e to the 2x plus 2 power? Well, follow the rule. It's equal to itself, e to the 2x plus 2, times the natural log of its base, which is 1, so I didn't write that up there. Well, then where did I get that 2 from? Oh, the chain rule. Yes, it still is there. And so do you see, I had to multiply by the inner function, which is 2x, the derivative of the inner function 2x plus 2. Of course, the derivative of that is 2. So where did that 2 come from? From the chain rule. Yeah, so as nice as e to the x is, we can't bypass the chain rule. Okay, how about the next one? Example 2 at the bottom, way at the bottom there. F of x equals e to the minus x. Okay, take the derivative. It's equal to itself, e to the minus x. And why am I multiplying by negative 1? Because of the chain rule. What's the derivative of negative x? Negative 1. And so how would we rewrite that? We would probably just say that equals negative e to the negative x. So you see how important the chain rule is? Yet, it always will be, but. Okay, now let's take a look at one like this. All right, now first of all, you notice in this problem, it's a weird exponent. I'm taking the function is 8 to the x squared minus 5 power. Now, first of all, is this an exponential? Yes. Is the base e? No. It's 8. Okay, so I got to use that other law, which says, again, how does that work? If I take the derivative of an exponential, I take it itself times the natural log of its base. All right, so itself, 8 to the x squared minus 5 times the natural log of 8. And there's that 2x again. Why is that there? Because I got to also, the inner function is x squared minus 5. And what's the derivative of x squared minus 5? 2x. Yeah.
When writing out the answers like that, do you want us to do the ln and 8 questions, or do you want us to actually start with
To show me that you understand it, this is wonderful. That's a good question. How does the book do it? I can't remember. I'm going to guess they probably want you to do the natural log of 8 on the calculator, but honestly, I'm going to have to look to check. So I'll tell you what. To answer your question, I should know this, but I don't. Let's take a look at one in the book and we'll test it out. If I can find the right one. Do they have any non-E's in here? They may not. That solves our question too. Right now, they don't have any non-E's. Now, see what they did is they took a more specific approach to the lesson than I did. I think this is better because you've got to know what to do when that base is not A. But they just stuck with all the E's. So actually it becomes a non-issue just because of the way they designed the lesson. So they don't have any non-E's. Okay? We don't have to worry about it. But I still feel I needed to teach it to you. Okay, here's an example from your book. Example 3, page 275. I want to take a look at that one. Example 3, and I'm doing part B. Differentiate the function e to the x minus e to the minus x all over 2. Well, first I rewrote the function just a bit. You notice I wrote it as 1/2 times the quantity. I didn't want to do that. I was chickening out of the quotient rule, I guess. Okay. So now, when you take the derivative, what do you do? Okay, well, you got to use the product rule. How do you do the product rule? The first times the derivative of the second plus the second times the derivative of the first. But what's going to happen when you do second times derivative of 1/2? That part is not going to do anything, right? Because what's the derivative of 1/2? 0. Okay. Now, you tell me, how do we take the derivative of e to the x minus e to the minus x? Well, e to the x, you want to take the really shortcut? It's just e to the x. Ta-da, that one's done. How do I take the derivative of minus e to the minus x? Well, it's itself times the derivative of its base, which is 1. And then why is this minus here? Because of the chain rule, right? And what happens? What happens when you take negative e to the negative x times negative 1? Doesn't it become plus e to the negative times a negative is a positive? Okay, and then it's still times 1/2. So you could write the answer like this. So it's kind of ironic. That derivative looks like all it did is change the sign in the numerator. So okay, so there's an example. Everybody get that? Not yet? Okay. Here's another one. We've got the function x squared times e to the x. Find f prime of x. Do we not have to use the product rule here? Yes. Product rule says first times derivative of second. Okay? First, x squared times the derivative of e to the x. Easy. E to the x. Plus the second, e to the x, times the derivative of the first. Okay, that isn't too hard. Sometimes you're going to see, I think, in the book, they will often simplify this answer because there's an e to the x in both quantities. They sometimes will write it in factored form and just factor out the e to the x. But there's certainly nothing wrong with this answer up here. And a lot of times when they have this chain rule, they like to what? You might write this as 2x e to the x. They might take the 2x and stick it out in front. That's, of course, the same thing. Here's one from the assignment. Let's take a look at this one. E to the 4x minus 2, that whole quantity squared. Okay. Well, how do you differentiate something to a power? Well, you use the power rule. So, what do? You take 2 times that whole thing to the 1 power. Okay? But then, isn't there a chain rule that needs to be done because there's an inner function there, e to the 4x minus 2. All right, well, what's the derivative of e to the 4x minus 2? Well, what's the derivative of e to the 4x? It's itself. And then the chain rule, wouldn't I have to multiply by 4? So do you see where I got this 4 from? Let me know if you did. In other words, how do you differentiate e to a power? You do absolutely nothing. You write it down, which I did. But then, is there an inner function up there? Yes, 4x. And what's the derivative of 4x? 4. So that's where this guy came from. Yeah.
So the e to the 4x, that's just the derivative.
This part right there is how you begin this derivative because it's its own derivative. But because there's an inner function, I now have to multiply by the derivative of 4x. And that's where that guy came from. Yeah. Okay. And then how did I get down here? Well, I just multiplied 2 by this. That gives me 8e to the 4x. And then I just left this in parentheses. Are you seeing that how I got that derivative? Okay. I had down 1 to 41 all odds, but we're going to do the every other again. I'm trying to, I don't know. I feel a little guilty about doing that, but at the same time, I'm trying to lighten it up a little because I'm sure you got plenty of stuff to do right now. So why don't we just work on this in class for a little while? Probably let you go early today. Does anybody have any questions? So, by the way, on the website it shows 1 to 41 odds. So I'm changing the assignment again.